Welcome back to another lesson with Learn Math by Example. Now, today we're diving into a real world challenge that will be your mathematical thinking to the test. We'll be exploring the fascinating world of sequences and series, covering how to identify their parts, determine general terms, and understand the difference between finite and infinite series. But first, let's set the stage with a captivating problem, the bacterial colony challenge. Imagine a research institution monitoring a bacterial colony. On day 1, they observe 100 bacteria. Critically, each subsequent day, the colony increases its size by 10% of its previous day's count. Now, our challenge has two parts. First, we need to find how many bacteria are present on the 8th day. And secondly, the colony has a critical limit. It can only sustain a cumulative total of 5,000 bacteria before crashing. So, based on this growth, will the colony crash within the first 15 days? This isn't just a biology problem, it's a perfect application of sequences and series. So, let's break down the foundation concepts needed to solve it. Alright, let's establish our core concepts, starting with what exactly is a sequence. Now, simply put, a sequence is an ordered list of numbers, and we call each number in that list a term. For example, 2, 4, 6, 8, and so on is a sequence. Now, each number here is a term. We denote it by un, where n represents the position in the sequence. So u1 is the first term, u2 is the second term, and so on. In our example, u1 is 2, and u2 is 4, and u3 is 6. A vital concept in sequences is the general term, often written as un. This is a formula that allows you to find any term in the sequence simply by knowing its position n. For our example 2, 4, 6, 8, the general term is un equal to n. If you replace n by 1, you get u1 equal 2 times 1, which is 2. For n equal 2, u of 2 is equal to 2 times 2, which is 4. You see how it works? Here is a crucial hint for your external exams. Finding the general term is a very common question in both paper 1 and paper 2. So make sure you master this skill. And while there isn't a single formula for un for all sequences directly in your IB formula booklet, understanding the general term is fundamental for using the arithmetic and geometric sequence formulas, which you will see in section 1.2 of the formula booklet. Next, sequences can be either finite or infinite. A finite sequence has a limited number of terms. For instance, 1357 is a finite sequence because it ends with 7. An infinite sequence, on the other hand, continues indefinitely. We usually indicate it with an ellipsis, 3 dots at the end. For example, 1, 3, 5, 7, and then 3 dots, which means it goes forever. Finally, let's talk about series. While a sequence is a list of numbers, a series is the sum of the terms of a sequence. So for the sequence 1, 3, 5, the corresponding series would be 1 plus 3 plus 5, which is equal to 9. Now we often use summation notation, a capital sigma, to represent a series. So if you look at the screen, you will see summation of k equal to 1 till n of uk. This means you are summing all the terms from the first one until the nth term. Now another important hint is always to distinguish between sequences. You have to know the difference between them. A sequence is just a list, but a series is the sum of the terms of the list. Now the IB Math AA formula booklet, again in section 1.2, provides specific formulas for calculating the sum of an arithmetic and geometric series. Now for your internal assessment, or IA in general, sequences and series are powerful tools. You can use them to model various real-world scenarios like population growth, compound interest calculations, or even the spread of information, allowing you to investigate cumulative totals or predict future values. Now that we have these definitions, let's apply them to our bacterial challenge problem. Now, in step 1, we identify the sequence type and parameters. We know that on day 1, there are 100 bacteria, so our first term U1 is 100. The colony increases by 10% of its previous day's size. This means we're multiplying the previous day's count by 1.1. 1.1 is called the multiplier. This constant multiplier tells us we're dealing with a geometric sequence since we are multiplying to get the next term, and our common ratio R is 1.1. Part A. Now, how many bacteria are present on the 8th day? In step 2 here, we're going to use the general formula for a geometric sequence. From the formula booklet, we know that un is equal to u1 times r to the power of n minus 1. So for the 8th day, n is equal to 8. So we substitute our values, we get u8 is equal 100 times 1.1 to the power of 8 minus 1. Using our calculator, this will give us 194.87171. Since we can't have a fraction of a bacterium, we're going to round it to the nearest whole number. So on the 8th day, there will be approximately 195 bacteria. Now in part B, will the colony crash within the first 15 days? This question asks about the cumulative total of bacteria, meaning we need to find the sum of the series. In step 3, in this case, we're going to use the sum formula for a geometric series. Again, from our formula booklet, the sum is Sn equal to u1 times r to the power of n minus 1 over r minus 1. Now we need the sum for the first 15 days, so n is equal to 15. Again, substituting n by 15, we get S15 is equal to 100 times 1.1 to the power of 15 minus 1 divided by 1.1 minus 1. Using our GDC, we finally get S15 is equal to 3,177.248169. Again, rounding this to the nearest whole number, the cumulative total after 15 days is approximately 3,177 bacteria. Now, comparing this with the crash limit, it does not exceed 5,000, which means that the colony will not crash within the first 15 days. And there you have it. From a growing bacterial colony, we've successfully applied our knowledge of sequences and series. Remember, the key is to first identify whether you're working with an arithmetic or geometric progression. Now then, if it's a sequence or a series, with those pieces in place, your IB formula booklet provides the exact tools you need. We learned about general terms like un equal u1 times r to the power of n minus 1 for geometric sequences, and some formulas like Sn equal to u1 into r to the power of n minus 1 over r minus 1 for geometric series. To check your understanding right now, you can go to our website and then check the lesson there. It will contain many practice problems. If you found this lesson helpful, please give it a thumbs up. Subscribe for more IB math content and let us know in the comments below if you have any more questions. Keep learning, keep practicing, and we will see you in the next lesson.